Hello there, this is Shannon Gracie. We are covering section 1.3 today, which covers the real numbers. Again, we're working from the Blitzer Introductory and Intermediate Algebra book. So when you're done with your homework, you ought to be able to define the sets that make up the real numbers, graph numbers on a number line, express rational numbers as decimals, classify numbers as belonging to one or more sets of the real numbers, understand and use inequality symbols, and find the absolute value of a real number. So why don't you go ahead and pause the movie and do the warm-up. So let's see how you did. Oh, here we go. If you remember from last time, we can go ahead and write this as one happy fraction where we're multiplying the 10 times the 3, and that's being divided by the 27 times the 2. Now notice I didn't multiply them out because I recognize that the 2 will divide out some of the 10 and that 3 will divide out some of the 27. So here we go. 2 goes into itself one time, and it goes into 10 5 times. And our 3 goes into itself once and into 27 9 times. So we'll end up with 5 times 1 over 9 times 1, which of course is 5/9. We'll put our happy box around the answer. So how'd you do? I bet you got that one right. Okay, so here we go. This one is an addition problem involving fractions. So here we go. You probably found that the LCD was 9. So here the only fraction that we need to adjust is the second fraction. And if we multiply that by 1, in this case as 3 over 3, we will get 28/9 plus 6/9. And then we can write that as one happy fraction with 28 plus 6 in the numerator and then our 9 in the denominator, which yields a result of 34/9. And 34 and 9 don't have any common factors except for 1, so we're all set. How'd you guys do? Great. Okay, so natural numbers and whole numbers. A set is a collection of objects whose contents can be clearly determined. The objects in a set are called the elements of the set. So here we go. Natural numbers. The set of natural numbers is. So here's our set notation, and you can list it. So 1, 2, 3, 4, and on like that forever, and in the set. So these kind of brackets are called, or this notation is roster notation. Roster notation contains a list, and we have a list of numbers in our roster notation. So if we were to graph this on a number line, right, we would have, if we start with some negative numbers, so here what the picture would look like is each time you're on one of the numbers, and only when you're on one of the numbers, you could actually put a point there and it would behave this way throughout. Now this one, make sure it's on that number. So this is the picture, and then I'm going to go ahead and do a little red at the arrow to show that it continues in that manner forever. All right, whole numbers. Now the whole numbers, the only difference between the whole numbers and the natural numbers is that the whole numbers, the very first element is 0, and then the natural numbers go on after that. So the set of whole numbers is roster notation. You start with 0, 1, 2, 3, 4, and on like that forever. That's what the dot, dot, dot means. And then again, making our picture, I can start with -1, 0, 1, 2, 3, 5, 6, and 7. So now we're going to be starting at 0 this time. Notice that none of the fractions or decimals in between each of these numbers is included. All right. So just to recap, the natural numbers are your counting numbers starting with 1. The whole numbers are the counting numbers or the natural numbers with an additional element of 0. All right, so here we go. Integers in the number line. The set consisting of the natural numbers, 0, and the negatives or opposites of the natural numbers is called the set of integers. So the set of integers is, again, what's this notation called? You got it, roster notation. So we're going to do our dot, 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 then comma, we'll go -3, -2, -1, 0, 1, 2, 3, and then it continues on in this fashion forever. That's our set of integers. And then, whoops, that's not very level. Do our number line to show what the graph looks like. So this time let's start it out over here. And then we'll go ahead and plot out the set of integers. And then it goes on in this fashion. Again, none of the numbers in between, but it'll go on in this fashion forever. Whoops, sorry about that. Okay, so here, let's look at this first example. Here's all these integers. Why don't you guys go ahead and graph each integer from this list on the number line below. Go ahead and pause the movie and do that. Okay, let's see how you did. So, the first one, 3, is positive. So positive numbers, remember, are to the right of 0 on the number line. So here's 3. So this 3 is here. And then -3 is the opposite of 3. So it'll be the same number of units away from 0 on the number line, but it's going to be on the left. Right? So -3 is located here. And then +5 over here. -5 over here. I'll get a good color to use. Whoops. Let's go to this and then I keep going to the wrong spot. Okay, so we'll use this purple, shows up fairly well. And then of course 0 is right over here. Now let me get that more on the, there we go. And let's use this kind of orange color for 0. All right, so how'd you do? Everybody do okay on that guy? All right, so let's go down here. The rational numbers. Now, what I want you to notice here is that, check this out right here. What does that spell? It spells ratio. And ratio can be written as a fraction. So rational numbers, really, the easiest way to think about them are numbers that can be written as a fraction, right? So that's going to include integers as well, because remember, isn't that the same as 2 over 1? So therefore that would be considered one of the rational numbers because you were able to make this ratio or fraction. So let's look at the definition. If two integers are added, subtracted, or multiplied, the result is always another, you got it, it's another integer. But let's think about this. Is this true when one integer is divided by another? Well, it worked for that one above, but what about, let's see, is 1 an integer? Good, yes. What about, is 3 an integer? Yep. And 1 over 3 is not an integer. So the answer to the question is no. So therefore, the set of rational numbers is the set of all numbers that can be expressed in the form a over b, where a and b are integers, and b is not equal to 0. So in Mathies, it would look like this. The integer a is called the good numerator, and the integer b is called the awesome denominator. All right. Are all integers rational numbers? I think we answered that before. Yes, and that's when we were doing the 2 over 1 is the same as 2, so yes. Which means that the set of integers is a subset of the rational numbers. Okay, here we go. Let's do a similar thing. We're going to look at these rational numbers and graph each one of them on the number line. So go ahead and pause the movie and do your thing. All right, let's see how you did. Negative 1/2 will be over here to the left of 0. 9/4, right? So that's 2 complete fours and 1/4. So 2 and 1/4. So here, that'll be 2 and then half of a half. It'll be about here. And -8 be on the left side of 0. That'll be our -8. And then -6 and 2/3. So will be 6 to the left of 0. And that's about 1/3, 2/3. So about here. It's good to know, where numbers are located on the number line. At least have kind of a gut feel for that. All right, so let's take a look. This one, we're dividing, and what we're doing is we're taking a look and seeing what kind of decimal we will have, what kind of decimal we'll have. So here, I don't know if you remember, but this is 3 divided by 8 can be written as, we put the 3 in here and the 8 here. And then, let's see, we'll probably need a few zeros here. Bring the decimal up here. So now 8 goes into 30 how many times? Good. 3 times, and 3 times 8 is 24. Subtract that and we'll get a result of 6. Bring the next 0 down, we'll have 60. There are 7 8s in 60, so we'll write the 7 here. 7 times 8 is 56. Subtract and we're going to get 4. Bring down the next 0. So this one was brought down here. This one will be brought down here. And there's 5 8s in 40. So we have a remainder of 0. So this one, since we eventually got a remainder of 0, 3 divided by 8 is actually equivalent to 0.375. This is considered to be a terminating decimal. So notice that 3 divided by 8 is the same as 3 eighths. So here, notice that we got, when we looked at this fraction, which is a rational number, we got a decimal that terminated. Okay. Now 3 divided by 11. Let's take a look. So again, the 3 will be in the box. And we have an 11 outside, so let's put a few zeros, see how we do. So 11, it goes into 30 twice. And we'll get a 22 when we multiply. And then we get a remainder of 8. Bring down the 0. 11 goes into 80. 7 times 11 is 77. And then we get a remainder of 3. Bring down the 0. 11 goes into 30 twice. Uh-oh, doesn't this look familiar? I think we just did this one. And look, we get a remainder of 8. Just for the heck of it, we'll take a look. Bring down the 0. You see, we're going to be getting this over and over again, this 2 7 business. So we get a remainder of 3 again. So here, what we have found is that this is a repeating decimal. So it turns out, again, do you see that 3 divided by 11 is a rational number? It fits the definition. 3 divided by 11 is the same as 3 11ths. 3 is an integer, 11 is an integer, so we have a rational number. So it turns out that repeating decimals are also rational numbers. So you can, I like to kind of write it like this, where you put the line over the repeating part of the decimal. And again, the 2 7 repeated. Okay, so here we go. Rational numbers and decimals. Any rational number can be expressed as a decimal. The resulting decimal will either terminate, which means stop, or it will have a digit or block of digits that repeat, as we saw above. Irrational numbers. Irrational numbers, they're basically numbers that aren't rational. So any number that can be represented on the number line that is not a rational number is called an irrational number. In other words, the set of irrational numbers is a set of numbers whose decimal representations are neither terminating nor repeating. So some examples of irrational numbers are pi, the square root of 2. If you go ahead and do that on your calculator, why don't you go ahead and get your calculator and evaluate the square root of 2. Okay. All right, so let's see what you found. What you probably found is something like this. You get 1.41, let me go ahead and just 414,213, and then it might have ended at 62, depending on your calculator. Well, what your calculator did was round that last digit. This number goes on and on and on forever with no repeating pattern. So that would be considered irrational, right? Okay. The set of real numbers. All numbers that can be represented by points on the number line are called real numbers. Okay. So let's just go through. This is sort of a recap of what we've been doing. Natural numbers, description. Remember, we can go 1, 2, 3, 4, 5, and on and on and on forever. What's that notation called? All right, yes, roster notation. So some examples of natural numbers. I don't know. 1, 11, 210,000. You know, I don't want that to look like a decimal point. It was just a mismark. 210,000. Those are all natural numbers. What was the difference between the natural numbers and whole numbers? Good. 0 was the first element in the whole numbers. So, why don't we go ahead and include that one? 0, 5, 83. These are all examples of whole numbers. Integers. So integers, remember we have negatives involved. So we do our dot, 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 -3, -2, -1, 0. 1, 2, 3, dot, dot, dot. And examples, we could have -50, 6, 0, -5. Those are all integers. Rational numbers. So remember, now here, this looks a little oddball, but this is our set notation. So for rational numbers, you've got a fraction. So a lot of times they say A over B, and then they'll say such that. So this line here means such that in mathese. A and B are elements of this is a little, we'll just say, we'll write it in words, are integers. And B is not equal to 0. There we go. So some examples. 5 halves, -8. How about the square root of 25? Does that work? Yeah, because isn't that just equal to 5? Okay. All right, irrational numbers. Let's write this one in words. The set of all numbers which are not rational numbers. These numbers decimal representations do not, actually it would be singular, decimal representation, do not repeat or terminate. So some examples. We had a couple already. The square root of 3. Pi, we mentioned before. There's a number called e. And then, I don't know, negative cube root of 9. Those all will have these, on the calculator, if you put them in, they'll end up as decimals that go on and on forever with no pattern. Okay, so example 4. Why don't you look at these? This set of numbers and list the numbers in the set that are, these instructions here. So why don't you go ahead and pause the movie and give this one a try. All right, let's see how you did. Natural numbers. We don't want any negatives or 0 or fractions, okay, that, don't end up as whole numbers. So let's see what we have. So natural numbers, I'm seeing, I'll just go in order of what I see here. 8 is a natural number. The square root of 100 is 10, right? So I'm going to write the square root of 100. And that's, believe it or not, folks, those are the only natural numbers in the set. Now the whole numbers, we know we're going to have 8 and the square root of 100 because the natural numbers are a subset of the whole numbers, but we will also have 0. And, just to be consistent, I'll go ahead and do them in the order that they appear here. Integers. Now, integers can be negative. And notice that negative 4 over 2 is really, you can also rewrite that, simplify that to be negative 2. So, negative 4 halves will work. 8 will work. 1/3 won't work because it is in between 0 and 1 on the number line. But the square root of 100 will work and 0 will work. Rational numbers, you notice what's happening. The sets are the numbers, are the number of elements that we're listing is getting more and more. So we have our negative 4 halves, 8, 1/3 is in the form of integer over integer, so that works. The square root of 100 works because that's 10, and 10 is the same as 10 over 1. 0 works. And 0.3 is 3/10. That is a terminating decimal, so that guy works. Okay, irrational numbers are numbers that are not rational, so that'll be the elements in the set that are not listed in the rational numbers. So here, the only one that'll work here is pi. And for the real numbers, that's like, the big mama of them all. So we're going to list all of these elements. So we'll have negative 4 halves, 8, 1/3, the square root of 100, 0, pi, and 0.3. They all work. Okay, now we're on to inequality symbols. So inequality symbols on the real number line, the real numbers increase from left to right. The lesser, and that should be an of, two real numbers is the one farther to the left on a number line. The greater of two real numbers is the one farther to the right on a number line. So here's some notation. If we have this here, that means A less than B. If there's a little line underneath, that means A less than, or it could be equal to B. And then if we have this one here, now notice that what you're seeing is that the point points towards the smaller number. So this one means that A is greater than B. And then again, if you have the line underneath, you're going to have A greater than or equal to B. So let's do our next example. We want to insert these, a less than or greater than between each pair of integers to make the statement true. So go ahead and try this one out. See how you do. Okay. So 3 is to the left of 5 on the number line, so 3 is less than 5. But 3 is greater than 0. Now be careful. Negative 3 is to the right of negative 5 on the number line. So negative 3 is greater than negative 5. Negative 3 is less than 0. Conversely, 0 is greater than negative 3. And negative 5 is less than positive 5. All right. Here we go. Last page. The absolute value of a real number A, denoted by these lines on either side of A, is the distance from 0 to A on a number line. Okay, so think about it. Is the output of an absolute value expression ever negative? When you're driving, let's say you go from home to work, and then you go from work to home. Do you consider work to home negative? No, right? So distance is always positive, and absolute value measures distance from 0 to a number on a number line. So therefore, you got it. The answer to this question is no. All right, so absolute value is an operation. Remember, it means the distance from 0 that the inside of these kind of absolute value bars, you can think of them as sort of jail. So to let it out of jail, you have to evaluate that operation, figure out the distance. So 2.5 is 2.5 units away from 0 on the number line, so it's positive 2.5. Negative 8 is 8 units away from 0 on the number line, so it's positive 8. All right, so here's an application. The table below shows the amount spent on iPad apps by Shannon's family during the months of May and July of 2011. So Shannon spent $48, Morgan spent $67, Rory spent $25, Aaron spent $32, and Nicole spent $12. So let's make a number line and we'll graph the dollar amounts on a number line. So here, you got to think about how you want to number your number line. Right? We've got all positive amounts, right? And they're fairly big numbers, so we might want to go by, I made a pretty big number line. I think we could probably go by fives. So 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. So 48 is going to be pretty close to 50 on the number line. So that'd be like 47, 40, probably about here, 48. Okay. So we'll highlight that one. So Shannon spent 48 bucks. And then Morgan, oh, look what happened. I hate it when that happens. We didn't go far enough, so I'm going to go ahead. That's why we use pencil in math. So this would be 55, 60, 65, 70. There we go. So Morgan spent $67, so that'd be about here. So there's Morgan's amount. Rory spent 25, so he's about right there on the marker. Aaron spent 32, be about here. Where'd you go, Aaron? There we go. And Nicole just spent 12, so she's down here. All right, so write the names in order from the least spent on apps to the most spent on apps. So it's easy since we've done this on the number line, right? We just look at the corresponding person and we can make our list. So notice that Nicole spent the least, so she'll go first. And then Rory, and let's see, 32 was Aaron. And then the yellow was Shannon. And Morgan spent the most. So here we go, we're all set. How'd you do? Great. All right, so have a fabulous day, and don't forget to do your homework. Bye.